So why on earth would we ever want to blur an image? There are generally two reasons why we might want to do this. One is for downsampling. If you have an image of super high resolution, maybe 5000 by 5000 pixels, you like to go to a web image of much smaller resolution, it's better to blur by a Gaussian before downsampling than picking each nth pixel. And the reason is called aliasing. If you pick each nth pixel without blurring, you sometimes get very funny effects because each nth pixel might by chance correspond to something that's somewhat irregular. So for example, if you have a checkerboard and you pick each other pixel, you might only end up with black pixels. The second reason is called noise reduction. In noise reduction, you respond to pixel noise that might otherwise make it hard to compute things like image gradients. If you blur the image first, you get a smoother result that isn't quite as pronounced, but it has much less noise in the image. So here's the original gradient magnitude image to fine edges, and here's the same applied to the blurred image. And you can see the original one is much more succinct, but it also is more subject to noise. So take the area over here, which has lots of image noise, and compare this to the area over here, which has many fewer edges. Same is true over here and over here. I wouldn't really claim this is a much better result. In fact, it looks kind of funny and very coarse, but it does have less noise. Just to complete the issue on blurring, what we just did is we took an image, we blurred it with a Gaussian kernel, and then we applied a gradient kernel. If you dive into the math of convolution, you'll find that convolution is associative. So you could apply this one to the image and then this one over here, or you can combine these two guys over here into a Gaussian gradient kernel and apply this Gaussian gradient kernel to the image. So F convolved with G is this big, maybe 9 by 9 Gaussian matrix convolved by a single +1 - 1 kernel G. And here's how this Gaussian gradient kernel looks like. It's really interesting. It is the same gradient kernel we had before, but smoothed now and spread out by a Gaussian. And it really responds to an area over here, similar to a Zobel operator, that might have a strong negative value. And the area over here on the right side, that is a strong positive value. So you can think of Zobel and many other kernels as a combination of smoothing and taking a gradient. I find this really interesting because we can now devise a single linear kernel that does both smoothing and fine gradients at the same time.